completely here on Moodle. Okay, viewers online who aren't here today. We are on Chapter 21 test hints, which are posted on Moodle and on my website and in your notes. And it is 6th period, and we're going to do as many of these as we possibly can. And you're not going to have to look at the side of my head this time, because I moved the camera. Right. Hopefully I'm actually not here. Alrighty. There are a couple questions on this test that are just picky book definitions. One of them is transmutation whenever we get to that. And that's typically a question that people are like, how did I miss this? And, what's the difference? So keep that in the back of your mind. Hint number 1, how a nuclide is identified. What is it? Nuclide is a very general term used to refer to various isotopes. But what makes one isotope or nuclide different from another? What makes one atom different from another? The number of protons. Number of protons. Now, with a particular nuclide, we're talking about isotopes as well. And isotopes are different how? Yeah, they can change up their number of neutrons. So, we could be considering a difference in both protons and neutrons. Protons make the element what it is. Neutrons affect the mass, and you may have several isotopes of the same element with the same protons, or you could have nuclides of different elements that have different protons and neutrons. Okay? How to read and identify the specific information found in a nuclear symbol. So, if we write, what did we have? We had iodine 127 over 53 in the sample problem we just did. What does the 127 mean?
Mass.
The mass number, which is what?
Protons.
The sum of the protons and the neutrons. What does the 53 represent?
Protons.
Number of protons. Atomic number. Okay, number 3 is similar to number 2. What if we wrote it like this, as I-127, or if we wrote out the word, iodine 127. What does the 127 mean still? The mass number. Okay? You're going to be good on that. Yeah. Number 4, how to define mass defect. We did just do that. It's the difference between what?
The protons and the neutrons minus
the relative mass of the protons and the neutrons added together minus the
average mass of the element.
The actual mass of the isotope, or the average mass of the element. Okay? So it's the difference between what the mass should be if we added up the weights or masses of each individual proton and neutron, and what it actually is. Because a little bit of that matter was converted into energy. Okay? Number 5. What high or low binding energy means for the stability of the nucleus. Wow.
Higher the binding energy, the more...
Higher the binding energy, the more stable. So that's energy released when the nucleus forms, and the trend in nature is to go to a lower energy state. So the more energy released, the more stable it's going to be. That's true in chemical reactions as well. All right, number 6. What is the best neutron to proton ratio for stability in low mass nuclides? 1 to 1 for the small ones, and what is it for the big ones?
1 to 1.5.
Neutron to proton ratio.
1.5
to 1. Think about that belt of stability. So what is the best arrangement for stability in terms of the neutron to proton ratio for the small isotopes and for the big ones? It's different. So the line of 1 to 1 ratio goes up steadily, but the belt of stability goes up. We need, as the nuclei get heavier and bigger, we need a few more neutrons in there to help regulate what's going on with the protons. All right. Number 7. What kind of forces and attractions exist between the particles in the nucleus?
Strong nuclear force.
The strong nuclear force is exerted by what? The neutrons exert the strong nuclear force because the protons are doing what to each other?
Pushing away from each other.
They're pushing away from each other because of what force? Electrostatic, yeah. The electrostatic force pushes all those positive protons apart from each other. They have the same charge. But the neutrons exerting the nuclear force pull them together. Okay? Mike, are you with me? Okay. Look, we're done with the whole page already on the test. Number 8. What the specific makeup of the nucleus that provides the greatest stability? The best ratios are what? Think odd and even.
Oh.
Oh, isn't it like numbers 20?
Think odd and even. What is the best ratio or the best arrangement? An odd number of each? An even number of each? Even. Think about one of the most common types of decay is alpha decay. What's spitting out there? Even numbers of neutrons, even numbers of protons. Okay? Even, even. You could have, what if you had an odd number of protons and an even number of neutrons? Or an odd number of neutrons and an even number of protons? Think about how many nuclei. Some nuclei are stable that way, but it's best to have even, even. Why? Because that delta stability is approach getting to 1 or 2 to 1. But odd, not that good. Alrighty. Number 9. How or why nuclear reactions take place and what is the result? Well, when a nucleus breaks apart, it's because it's trying to be what?
Stable.
Stable. So we're trying to get to higher stability, and the fact that all of this energy is released in this process means that the atoms are also trying to get to what?
Stability. No.
In terms of energy.
Unexcited.
Unexcited or lower energy. Okay? So they want to be more stable and lower energy overall. So they may release a lot of energy to get down to the more preferred state. Alright, 10, 11, and 12 are balance the following equation. In fact, all 3 questions, balance the following equation, balance the following equation, balance the following equation. Those are examples. For instance, the radon one that we just had on the checkpoint. That would be a good example of one of these types of problems. So you're going to have to know alpha decay, beta decay, and maybe neutron, release of a neutron, or bombardment by a neutron. I think you guys have been good with that as I've been watching work on stuff, so I'm not too worried there. 13, the definition of nuclear decay. How does nuclear decay happen? Well, that's what's given off. Is it predictable?
Yes.
No-ish. It's a spontaneous decay. It just happens. We can't say, ooh, that atom looks like it's getting ready to decay.
Particular
No.
atoms.
Right, not particular atoms. It's like, boom. Spontaneous decay that results in what? Daughter nuclei, particles given off, whether alpha or beta, maybe some gamma radiation, and a smaller, more stable nucleus as the result.